Okay, welcome to the first tutorial of topology and condensed matter physics. I am Sunit Das, uh, final year research scholar from IIT Kanpur. So basically, there are I mean 8 weeks. This is a 8 week course, and there will be eight uh, tutorials. Okay, I do not think that there will be any more. I mean, later, if needed, we can have one more at max. And each each week will have some assignment which you need to solve and submit. You are actually instructed not to solve the assignments actually. Okay, but this is a very advanced course. Okay, topology and condensed matter physics is something that is still developing, and it's a very active research area. Okay, it's not something that you will find in classical books, uh, condensed matter books, let's say Ascot Marmin or Evac and Luth, and any other books actually. There are few books that came recently. You will find some bit of it, but again, the concepts are incomplete because they're still in the development phase. So there is not much other problems that we can do. The similar problems that will be given in the assignments is going to be, I mean, it will keep popping up. Okay, there is not really very, I mean, unlike the other mathematical course or other basic level course, let's say. Okay. Uh, so I am not really sure how should I proceed because given that we cannot solve the assignments fully, so yeah, so before going to do anything, I think it is better to have a sense that from which background you people come from. Depending on that, we can decide actually. So you just unmute, please unmute yourself and introduce, please. That will give me an idea ki where should this tutorial conducted. Can you just one more time?
Hi, I'm Saurav.
Yeah,
I'm in my second semester of Masters in Physics.
okay. Then Sasikant, please feel free to question and yeah,
Hello, sir. My name is Shashikant Kumar. I am MSc from Central University, South Bihar.
okay. So other ones, Sachin, and
Yes, sir. Good evening. I'm
yeah.
Sachin Rajarma, just graduated from IIT Delhi Masters in Physics. So
So you're doing PhD
that's
or just to know this topology?
no, sir. Actually, I was doing a short-term project under like some professor. So right now I'm on a vacancy because a lot of time I have spent living in college. So I want to have a short period of vacancy for my son.
Mm.
So that's why I tried to enroll in some. Even my master's project was under condensed matter theoretical physics. So that's why
Okay,
I
nice,
tried to enroll.
nice. Uh, Angsu Pia,
Yes, sir. I'm also in second semester of masters in physics.
okay. Then last one, Charisma, I think. Okay, so most of them of you are actually in masters, or basically, yeah. Tell me. Anyway, I think it is better. I'm muting myself. Okay, so most of them you are from second year masters, right? Or yeah, yeah, it's okay actually. We can go ahead. So, so what do you expect from these tutorials? I mean, yeah, I'll do something from my side, but it is good to know what you people expect. Depending on that, we can decide.
Maybe we must be expecting some mathematical touch of what because this is something related to condensed matter. So in mostly in masters, like there are not much many course offered related to topology and the condensed matter theory. Since this is an advanced course, not all the universities like perfectly deliver it. So I might be, from my opinion, I might be expecting some mathematical aspects and the current ongoing things which we are like right now. AI summit is going and quantum computers and all the things. So might be that something related to that things we are going to get aware in this course as well eventually. But that's the goal. That should be the goal from my side that I might be able to get something on.
Okay. Okay. Any other opinion from other people? Okay. So these tutorials are actually question answer forum. Okay. If you see the guidelines of NPTEL, that is also they mentioned it clearly. So primarily there will be 4 or 3 lectures roughly each week they will release, and then there will be some assignments, sometimes based on those lectures, sometimes based on the previous set of lectures actually. So most of the time this will happen that this week's assignments will be based on previous week's lecture. That's the that's usually happens. And these tutorial sessions are primarily sort of doubt clearing session. Okay. Uh, so feel free to ask questions, and given that these are pretty advanced questions, there can be questions which uh, in fact, there is a high probability that there will be some questions which we will not, myself will not have an answer to. Okay, but I can always go back and read and give uh, some ideas actually. Uh, yeah, so I generally what I plan to do is that uh, so the course has a, I mean, so definite structure of it. I mean, given and there will be a lot of calculation which will be skipped in the course as well. Okay, and that calculations actually you should do it. I am also not planning to every calculation. It's very impossible for a 2 hours of tutorials per week also. Okay, and some calculation you actually need to do to get a feel of what is happening. uh, what I largely plan to do is that in each subtopics, so there will be quite a few big subtopics, starting from the topology, introduction to topology and why it is relevant in condensed matter physics, and then there will be extensive discussion of SSH model. That's the kind of preliminary model to have an understanding of the topology, and then quantum Hall effect as a fast topological insulator, experimentally realized. Will And then there will be some bit of quantum anomalous Hall phases. So let me write those things. Now these terms will appear unknown, possibly, but then eventually it will be clear. Okay. So initially, I mean topology and why do I need to study topology, right, in condensed matter physics? So that's the first question, and then maybe second, quantum Hall effect. And quantum Hall systems are the first topological insulator realized in I think 1882. Okay, von Klitzing actually, and then something I think fractional quantum Hall effect. This we can call integer fractional quantum Hall effect. And in between somewhere we'll read some bit of symmetry classification. Okay, and then we'll or actually vice versa. Actually, I think the lectures are organized as integer quantum Hall effect and then quantum spin Hall effect. And in one of the week's lectures, there is something also quantum anomalous Hall insulator. anomalous Hall insulator. Okay. And then I think the last set of lectures are on fractional quantum Hall effect. Okay. So what I plan to do is that I I'll sort of semi-solve those assignment problems, not fully solve. Okay. So that since it's a part of your grading system, and from my sides there will be I'll try to have these particular lectures uh, kind of in a more detailed way and from a more pedagogical point of view. Okay, not all the lectures will be like that. For example, fractional quantum Hall effect is very involved topic. Okay, it requires heavy math, but lectures in the NPTEL also I mean avoids that heavy math, because practically it is very difficult to uh, cover everything of fractional quantum Hall effect in 2 weeks even, 4 or 8 I think 8 lectures. Okay, so that's what my plan is. So we'll do some bit of theory. Uh, I'll try to sort of see that if it doesn't exactly overlap with what has been already taught in the lectures already, or even if it is, then I'll try to be more detailed within the 2 hour span of time as much as possible. Okay. Okay. So have you guys seen the week one lectures, let's say? See, because these are primarily question answer sessions, okay? Tutorials are designed to have question answer. So, okay, fine, it's fine. So actually, it's better if you actually see the lectures, and then if you have any question, you come up with that question set. So if you have any questions, please unmute and ask. Okay, if there is no questions, then let me start. So I'll give you a brief overview for first lecture. Actually, I think it is better to have a overview, okay, before going into the much more details. Okay. Uh, so so the topic is topology and condensed matter physics, right? So there are two terms. One is topology, of course, and then another one is condensed matter physics or phase. Now, in condensed matter physics, we study a lot of things, right, of condensed state of matters. And then few primary examples will be, of course, the transport. That is one of the most prominent study. In fact, we do also in our laboratory. And then there are various aspects of transport itself, but then it is important to distinguish it from a different aspect, that there is superconductivity. And then there is magnetism and many other things, right? So basically, so we are interested broadly, if I speak about condensed matter physics deals with different phases of matter. Of course, it literally mostly deals with condensed phase, but then different properties within the condensed phase itself, right? And then topology is something, it was sort of primarily in studied in a branch of mathematics. So topology is a branch of mathematics actually. It actually used to study different shapes, different geometric shapes, and how they can be deformed and what are their characteristics and so on. Okay, so this is a very difficult, I mean, very, so the topology in itself is a very deep topics or sub branch of mathematics. Okay. Now, the question is, why do I need the concept of topology, and how they appear in condensed matter physics? How does this help, right? So to understand that, I think so we'll go back and start from different phases of matter, what we know. Okay. So there are different phases. For example, so if we start from the very basics, we have solids and then liquid and then gas, right? And of course, plasma is there, but then leave it for now. So we can continuously go from solid to liquid and then liquid to gas. So these are classical phase transition we all study in our preliminary courses. And of course, I mean, if you talk about what is the key underlying parameter that defines the solid, or that you can sort of tune and then go from solid to liquid and gas, one is of course temperature, right? And then it you can also apply pressure to decrease the volume of a gas and then go back to solids, and then it can also go back to the I'm sorry, from gas you go back to liquid and then you can come to solids. Of course, there are exceptions and there are a lot of caveats, but largely, if you think of solid, liquid, and gas, the one key parameter is the density, right? So my handwriting is pretty bad in the board, pardon me. But for solid, you will have a highest density, and then liquid will have lower density, and then gas is sort of more, I mean, very less density, right? And you can apply temperature or pressure depending on this. You can you can have transition from one state of matter to another state of matter. Now, these are sort of classical phases, and since we are studying condensed matter physics, we are already here only, okay? Solid state of matter. Now, in solid state of matter, there can be a lot of other phases, and as I talked about, one is superconductivity, and then another one is magnetism, right? Even in magnetism, you can have different phases, and the canonical phases in magnetism, we know that paramagnetic state, and then we can have ferromagnetic state, and then diamagnetic. There are other states, for example, you can have antiferromagnet, and then there are other different states actually, even within the magnetism. Okay, there nowadays there in the literature there is something called alter magnet and so on. So this particular magnet is, by the way, maybe 6 7 years old. Okay, it's a very recent one. But anyway, but these three are the main. Paramagnetic is something, again, you have magnetic moments, but they are randomly oriented, so that you do not have any net magnetization. So if I call PM as a paramagnetic, then you total magnetization M net will be 0, and then ferromagnetic FM, you'll have some net magnetization not equal to 0, and then diamagnetic also have do not have net magnetization, but they also repel the magnetic field and so on, right? So basically these phases are determined by, you have a macroscopic order parameter. So these are called order parameter. So which means that for a ferromagnet you have a this order parameter to be non-zero. You have a total magnetization, and then for paramagnet you do not have any order parameter, or total magnetization is non-zero. Okay, and in all these phases, actually the symmetry plays a very important role. Okay, so by symmetry I mean there are a lot of other symmetries, but then few fundamental symmetries will be, one is, let's say, inversion symmetry, and then time reversal, and there are other symmetries as well. For example, in superconductivity, you will see that ion gauge symmetry and so on. Okay. Now, if I since we are talking about magnetism, if we see, if we think in terms of order parameter, you will have something like this, that you have a ferromagnetic states, let's say. This is your order parameter, net magnetization, and then suppose you are changing the temperature, right? So somewhere here you will see the transition. Okay, so this is Tc. So T below Tc you will have ferromagnetic state, and then T above Tc will have non-magnetic or paramagnetic, let's say, or you can call it non-magnetic. Okay, so for the example of solid to liquid to gas, we had density which was very high in solid, and then somewhere I mean in between in the liquid, and then very low density in the gaseous phase. For ferromagnet to paramagnet or ferromagnet to non-magnet state, we have something called order parameter or magnetization, right? Which is some finite value in the ferromagnetic state, and then as you increase the temperature, it decreases, and then at certain temperature, which we call Curie temperature, okay, it actually vanishes. The magnetization is zero. And then, of course, as you keep increasing the temperature, it remains at zero non-magnetic state or paramagnetic state. Okay, so this particular this is what happens if you think in terms of order parameter. If you think in terms of symmetry, uh, so you ask the question that what was the symmetry in this state versus in this state, right? It turns out that it is time reversal symmetry. Okay, so you have a material, let's say solid state material. There are, of course, when you think every time we'll be saying it's a system, or in our mind it is a periodic lattice with some lattice structure and so on, right? Periodically arrange some atoms. So the local spins of these atoms are, let's say this was my ferromagnetic state. So though the local spins are arranged in such a way that I have a m net to be non-zero, right? And then if you go in a paramagnetic state or non-magnetic state, the local magnetization vectors are arranged in such a way that overally you need to have uh, total magnetization to be. So total magnetization is sum of SI, let's say, spin vectors. So these are SI, okay. It is zero, okay. And it turns out that in this ferromagnetic phase, we have a time reversal symmetry broken state. So in short, we will write TRS as the time reversal symmetry. Okay, in this phase, time reversal symmetry broken, and then in this phase, paramagnetic phase, we have a TRS preserved. And another easy way to look at this, or another easy way to say this TRS broken or TRS preserved, or the symmetry in the ferromagnetic and let's say non-magnetic case, is that spin rotation symmetry. Okay. In the ferromagnetic case, you do not have this spin rotation symmetry because all spins are aligned along single direction. Okay. These are the simple picture, but in realistic magnetic materials, you can have something called domains. So what does that mean is that you have different areas of the samples, and then the spins are arranged in this domain, let's say along this direction, in slightly, I mean, at slight angle with this, and then in another domain there will be something like this. Okay, but then overally the m net is not going to be zero. If you sum up all the spins, it is some finite value. Okay, so there is no spin rotation symmetry, meaning you cannot get back to, so by rotating spins you cannot get back from here to here or here to here. You can get back, but then overall, as the overall net magnetization is non-zero, then if you rotate the spins, so basically what you're trying to see is that by rotating the spins, can you create a system where you will have m net not equal to zero? But that is not possible here in the ferromagnet. Okay, that's why we call it rotation symmetry is broken in ferromagnet, whereas paramagnet you can think of. So these are the simple pictures to understand. Okay, you can think of paramagnets are something like that, so that the overall spin actually vanishes, so that m net is zero in paramagnet or non-magnet, so that spin rotation symmetry is there. So if you rotate spins and then overall you will get m net to be 0. So the reason we are saying all of this is that a ferromagnet and a paramagnet can be differentiated by the total magnetization, and the underlying symmetry of this particular distinction between ferromagnet and paramagnet is that for ferromagnet we do not have spin rotation symmetry, and for paramagnet we have spin rotation symmetry. Or if we talk in terms of time reversal, in ferromagnet we have time reversal symmetry broken, and then for paramagnet we have time reversal symmetry preserved. Okay, so this was the story of let's say uh, magnetization or ferromagnet and non-magnet. But then if you think of the order parameter, how this ordered phase arises and how do we characterize this ordered phase. So for ferromagnetic system, the order parameter is m. Okay. So there is something called Landau theory. Okay. So this you must have read in your statistical mechanics course, right? Landau theory. So what this tells us is that you have a Landau free energy for a magnetic system. The thing we study in a usually our course is that Ising model, right? So we have free energy something like this: A m square. M is the order parameter or magnetization, and then plus B m to the power 4. And we solve this. I mean, minimize this Landau free energy, and what we get something like this. It should be symmetric. Okay, anyway. So this is land of free energy versus m. So this is, let's say, plus 1 and minus 1, and this value is 0. Okay. So m can have three values: plus 1, 0, minus 1. Okay. So what really happens for if you go below some particular temperature Tc. So let me draw. Okay, so this is, let's say, T less than Tc, T equal to Tc. This would have been more flat, but this is T greater than Tc. So as you, decrease the temperature from you are starting with T greater than Tc to T less than Tc, your M, by solving this particular equation or the Landau free energy by minimizing it actually. So you are having the zero solution here, right? So here you have the free energy and then order parameter to be zero. Minimum free energy is at order parameter zero. That means the system in a state where m equal to zero minimizes the energy of the system. As you know, all systems wants to minimize its energy, minimize its entropy. So that's the stable state. And this is the case for non-magnet or paramagnet when you are greater than T greater than Tc, right? So this particular curve. Now, when at T equal to Tc, still you have a very one single point. You're still at m equal to 0. That's the transition point actually. Again, the m equal to 0 state minimizes the Landau free energy. So the system have m equal to 0 state at T equal to Tc, let's say. Okay. Uh, the moment you go T less than Tc, you have a two this type of structure. Okay. So the black color where two different state or two different minima appears. So one is m equal to plus 1. Again, for this m equal to plus 1, Landau level, Landau free energy is minimized. Okay, minimum. And then m equal to, for m equal to minus also the Landau free energy is minimized. So system can be at m equal to plus 1 or at m equal to minus 1 once you go below T less than Tc. Okay, so and in reality, what really happens is the system is at either in this state or in the vice versa actually. uh, Either in this state, if you call m equal to plus 1 to be off state, meaning you have a material and then all spins are effectively m is, let's say, off direction, and then there is another state with the same probability that the system is in the down state. Okay, meaning m is effectively down. So once you go below T less than Tc, the system chooses one of these ground state, either this one or this one. So this gives you an idea that this system itself breaks the symmetry in a sense that this particular free energy is actually if you plot in 3 dimension for a 3D material, let's say, or M can have mx, my, and mz, then this Landau free energy appears to have appear in a circle, okay, or in a 3D space. So you rotate in the whole 3D space, you will get different value at 360. So what this necessarily means is that when you say that we have a ferromagnet with, let's say, some m equal to some m0 z cap along, let's say, z direction, it necessarily means that system chooses this ground state m equal to plus m0, this one. Okay, there is a degenerate state at m equal to minus m0 z cap also, but system didn't choose. But again, there are a lot of other caveats, for example, anisotropy energy and so on and so forth. But this already gives you an idea that in the ordered phase. So ferromagnet means in the ordered phase because order parameter is non-zero, obviously. So in the ordered phase, system symmetry is broken, or system chooses one of its ground state. So you see the correspondence, right? Earlier we are talking about spin rotation symmetry is broken in ferromagnetic state. So this can also be sort of reconciled from here, that because system chooses one of its ground state. So either this one or this one, up or down. Okay. Okay, so these were a conventional way of understanding phase transition. Sorry. Uh, okay, so these are conventional ways of understanding phase transition. It dates back to very old days. So initially we studied solid, liquid, gas, and so on, and then later came the idea of Landau free energy, and then Landau-Ginzburg theory, and so on. Right? That's how we understood the conventional phase transition in solid state system. Uh, I'll just briefly talk about superconducting phase also, because that is another important phase. So superconductivity. So in superconductivity also something similar happens. I mean, again, there you can write Landau free energy for superconducting states, and then if we call it, what should I call it? There the order parameter is psi. So psi is Cooper pair wave function, let's say, or the, I mean, superfluid order parameter. So psi is non-zero in superconducting state. SC is abbreviation for that, and then psi is zero for I mean, normal state. And how do you experimentally see superconductivity is that, again, this was, I think, 1911, observed by Kamerling Owens. I'll write Owens only. So what he observed is, I think, in mercury, so he was decreasing the temperature. So this was temperature versus resistivity, or yeah, resistance. So there's some resistance at finite temperature, and then at some particular temperature it drops very quickly. Okay, so here Tc is the superconducting transition temperature. So, so what he observed is that at Tc we have a, I mean, the resistance is immeasurable. Okay, it's never perfectly zero, but then within experimental accuracy and then measurement, whatever our instrument can measure, it was perfectly almost zero at, I mean, below Tc. So that's the transport response. But when we talk about theory, we talk about Cooper pair density, and then I mean solid, I mean superconducting wave function, which is a macroscopic wave function with a single phase, okay, in the whole system. So there also system chooses one of its ground state. So this one or this one, okay. And again, there is a symmetry breaking in the system. So so again, the similar thing repeats actually. So this is, let's say, T greater than Tc, and this is T less than Tc. System chooses one of its ground state. Let's say this one is chosen by system in the order state. So it breaks the symmetry, right? All of this story I am telling because there is a single important thing to point out, is that order parameter or the ordered phase are essentially accompanied by some sort of symmetry breaking in the system. It turns out that for superconductivity, there is something called U1 gauge symmetry. Okay. We'll later come back if we get time how to call U1 gauge symmetry and so on. It's a phase of wave function, let's say, e to the power I phi and then psi, or the chi part of it. Okay. So psi is some eigenvector and then some phase of it. So this particular gauge symmetry is broken in this ordered phase. Okay. So the idea is that whenever you have some ordered state in condensed matter, whether it is magnetism having finite magnetization or superconductivity with finite Cooper pair density or superfluid stiffness and so on, you essentially break some symmetry and then you go to the ordered state, right? So that's the conventional way of defining phases in solid state system, and it is called uh, Landau paradigm of phases. Okay, in solid state, because whether you talk about magnetism or talk about superconductivity, all you can phenomenologically understand from a Landau-Ginzburg theory or Landau theory. Okay, so that was the conventional sort of theory established, and it was pretty very successful in explaining a lot of things. I only talked about the transition, right? Your magnetization is zero or non-zero, but then whenever there is a phase transition, there is associated length scale divergence and critical exponents and so on. All of those things are pretty much very nicely captured. At times it also failed, but largely the behaviors were captured by Landau theory of phases actually. Okay. Now the question comes then that if Landau theory is already successful at so many levels, defining different phases of materials in solid state system, why do I need to study something called topology, right? Uh, so it is actually topology and condensed matter physics, or you can call it topological phases of matter. Okay, topological phases of matter is more broad because it can extend beyond solid state or condensed matter physics. So yeah, so so far so good. Landau theory sort of explains those. I mean, conventional superconductivity and magnetism, but there are systems people observed which cannot be explained. What we usually have seen, that there is a order parameter, order goes to non-zero at in ordered state, order goes to zero in disordered state. I mean, yeah. Uh, and one primary example that kind of initiated the whole field of topology in condensed matter physics is that quantum Hall effect. Okay, or modern day you can also call it Chern insulator. So to understand why do I need the idea of topological phases, is that then necessarily there are some phases in materials which you cannot explain by this Landau paradigm, okay, Landau theory of phases. And the first experimental observed system, as I call it, I mean, told it that quantum Hall effect or quantum Hall insulator, or you can also call it topological insulator. These are two different things, but uh, for our purpose, for now at least, it is fine. Okay. Uh, so why do we need the idea of topology in condensed matter? So imagine you have a I mean insulator. So okay, so let me go back to a little bit and then explain. Okay, so imagine you have a solid state system in your lab, a material is there, and then you apply some bias in it by applying some voltage, right? And then you measure some, I mean, the response of it. Either if you are doing four probe, then you will have leads here, and then you will measure the voltage here also. So you are applying some current, right? And then you want to measure the voltage, output voltage and input current, right? So that's the basics of solid state transport. Now imagine a system. Now, okay, so this type of transport will usually happen in metals, right? That we all know, and the typical metals that we know of is, of course, copper, aluminum, and so on and so forth. The electrical wires in our house or everywhere is just some of these elements. So they conduct electrons almost freely because they have a lot of free electrons. And once you apply some external potential drop between these two end of the wires, they will conduct electricity. So that's the part of metal, right? Now there are some materials which are insulators, right? Insulators, where if you apply electric field, they will not easily respond to have current actually. So yeah, so in the typical, I mean the picture that we know of is that, let's say this is conduction band and this is, let's say, valence band, right? And then in metals they overlap, and in semiconductors they have little bit of I mean band gap. Again, conduction band and valence band. So that once you apply electric field or external voltage in this semiconductors, then you need to after a certain time, I mean time means the voltage. So this will be what, current versus voltage characteristics. So maybe for semiconductor something like this will happen, right? Uh, Something like this. So after a certain initial cutoff voltage, you will get some output current which you can measure as a voltage. And then for insulator, you have a very high band gap, so that it is very difficult to get conduction through this insulator, right? So they have a large band gap. And this is usually of the order of electron volt. This has no band gap, and then the band gap for semiconductor varies, but then it is essentially less than electron volt. Or even it is order of electron volt, it is few electron volt, maybe 1, 1.5 something. But this have, let's say, 5 electron volt and so on. And there are real examples of having insulators with 5, 2, 3 electron volt. Okay, so these are the story of metals, insulator, and so on. But there are some insulators when if you apply current, let's say, or let's say voltage, external voltage. Yeah, so basically this is input, and then you are, let's say, measuring some Hall voltage. Hall meaning you are applying current in this direction and you are measuring voltage along the perpendicular direction. Okay. We all know Lorentz Hall and same configuration here. So you are measuring some voltage, P output. Okay. It turns out that you are dealing with insulators. Okay. So this is an insulator material that you know. You apply some input current, but then you get finite voltage. Okay. V output is not equal to 0. And these are very particular insulators. It's not conventional insulator that we know of in our day-to-day life, or let's say whatever we have been taught in maybe at the level of Ascot Marmin or Ibak and Luth or any equivalent books. Uh, so what we have is something surprising. You are dealing with an insulator, but then you are getting a Hall current, right? That's not something that we get, right? Even in the Lorentz Hall effect, what you do is that you have some, let's say, material 2D or 3D. Usually, Lorentz Hall effect is studied in either in semiconductors or in metals, actually. So you apply magnetic field along the perpendicular direction, you apply electric field, and along the perpendicular to both of these electric and magnetic fields. So let's say this is out of plane, this is along maybe. So if I draw it, so this is, let's say, Z and Y, and this is X. So you are measuring voltage along X direction output for Lorentz Hall effect. Okay, and you are dealing with either metal or semiconductors. So you are getting Hall voltage along perpendicular to both the magnetic field and electric field, which is fine. We understand this pretty well, in fact, fully. And you can understand this within the Drude theory itself, right? But this situation is completely different. You are dealing with an insulator, you are applying current, and then you are getting voltage, perpendicular voltage or Hall voltage, let's say. So Hall voltage. Uh, the problem is, how do I characterize this, or how do I distinguish these two phases of insulator? That's the key questions. One of the earliest question, I mean, uh, to address the importance or to understand the importance of topology in condensed matter physics. So what we're trying to say is, in simple words, you have a insulator something like this. You have a band structure. So this is, let's say, energy, and this is, let's say, K, momentum. You have a band structure something like this. What we call insulator is also called band insulator. Okay. In more, I mean, formal language, it is band insulator because both the bands are not touching each other. Rather, they are gapped by some band gap, right, in the energy space. So this is the total uh, amount of band gap energy, right? So this is also called band insulator. And then you have some insulator which are gapped in the band itself. Uh, so again, so this was the, let's say, conventional insulator, and this is topological insulator. Okay. The only difference, actually, there are many differences, but then key difference is that here you will get Hall voltage to be 0. Here you will have some Hall voltage, okay, not equal to 0. But then the important common thing between these two is that both of them are insulator. If you look at the band structure, so this is the energy space and then this is the K, right? Uh, how do you tell these two insulators are different? I mean, they are same, right? You have a band gap here and then you also have a band gap here. So this is one of the fundamental questions uh, which tells us that there is something that we need to know so that we can understand this particular insulating field where we get some finite Hall voltage uh, even if we have a band gap. Whereas in this particular system, we do not have any Hall voltage. Okay, so that's the key question. One of the key question which forces us to rethink the way we understood different phases of matter. And there are different topological phases. So this topological phases and topology and condensed matter physics deals with this kind of characterizing this kind of insulator. In fact, it doesn't only concern about insulator. There are some sort of semi-metals or some metals even, which show different characteristics. So this is one, I mean, primary example which have been observed in the earliest times, 1980 or something. But there are different systems which you cannot understand from the conventional point of view. Okay. To understand this kind of insulator, we actually need something called topology, and that's how the field sort of that's sort of the necessity of understanding or studying topological phases of matter. Okay. So this was the broad picture. If you have any question, please ask, because I think, it is important to have a broad overview why we need to study topology, right? Uh, there are many answers to this, but then one of the basics answer is this, that how do I characterize between an insulator which doesn't have Hall voltage, being an insulator, and one another insulator which even after being an insulator, it carries Hall voltage or Hall current actually. Okay, so that's the key question. If you have any question, please ask. Okay, fine. Okay, so uh, that's what we'll do in our You can just unmute and ask actually. Okay. Actually, in the chat box, okay. So there is some questions. Uh, Sorry, what is the question? The last lecture in week one is tenfold ways, but then it is starting with the assumption that the TRS and charge conjugation is already done. I think the ordering has some problem with it. Okay, yeah, that's true actually. Tenfold way cannot be the week on lectures part. Okay, yeah, fine. Yeah, that this is a I think mistake from NPTEL side. Then the next question is it the same band what we have in the conventional one? Same in what sense? So what I tried to say is that by looking at the band structure, right? So there is of course I mean complicated band structure in real materials. But if I draw kind of realistic, little bit realistic, of course. So this is the energy and then momentum. We have some bands, let's say, and then you have another bands, and then Fermi energy, up to which the electrons are occupied at zero Kelvin. Uh, so, so when you talk about metal, you put Fermi energy anywhere. You put here, here, here. It doesn't matter. You always get some electrons to conduct, right? So how does the conduction actually happen? So imagine you have a Fermi energy here. Up to this is filled, right? At zero temperature. So you apply electric field. So essentially you are giving some force to the electrons, force of let's say minus E and electric field. So these electrons go to a higher state. So there are already states here, right? Because it has some allowed energy. Uh, so electron gains energy or it goes to a I mean unoccupied state, and that's how the uh, uh, I mean the conductivity arises. You get current once you apply metal in a metal, copper, aluminum, so on and so forth. Now, so I was trying to say, yeah. So what I was trying to now for an insulator, if you look at the energy versus K plot, you will see something like this. Of course, you will not see discrete, something discrete in real materials. There will be other bands and so on. But for simplicity, this is fine. Suppose so for insulator, what necessarily means is that your Fermi energy is somewhere here in the gap. Okay, so that if you apply electric field or external perturbation, you have no electron here. So at this energy, so this is let's say Fermi energy. At this energy, there is no electrons. So obviously, then there is no conduction of electrons. So no current, right? So that's what the conventional insulator is. Now something if I talk about topological insulator as well, in short we'll write TI, okay, topological insulator. Uh, Something same actually. There is not much difference. In fact, you can have this band structure itself. Uh, by looking at the band structure, that is the point. That by looking at the band structure, you are not able to tell that it will conduct Hall current or not. But once you measure, so here also you have Fermi energy. It is not that it is here. Okay, you are still in the insulating regime, so that your Fermi energy is here, and you apply electric field and you get a Hall current. Hall current is not equal to zero. So that is the key point. That by looking at the band structure can be same, but you have a different response depending on which regime you are. Either you in the topological insulator phase, you have Hall current, and here Hall current is zero. Okay. So the question is, how do we characterize these two phases? characterize or differentiate to insulating. Okay. And it is this question that we deal with in the topological, I mean, topology in condensed matter, that what else we need to look at of the system so that we understand this particular phase well. This particular thing we really understood. I mean, pretty much understood. It's a band insulator, so Fermi energy lies in the band gap. There is no states to conduct, so we do not have any current. But if we think from the conventional way, then here also it is the same. We have a Fermi energy lying in the gap, so there should not be current, but there is current. So how do we understand this? Okay, I hope this is clear now. Or any questions? Please ask. Uh, so the question is, what is the necessity to apply topology for an insulator? This is the necessity that we want to understand the system better, that what is really happening and how do we understand this second case where even if we think or if we look at the band structure, it is insulator, still it is carrying current. How do I characterize this and how do I understand this? What is carrying current and then other questions. So that's the necessity of applying topology in an insulator. Uh, this will be much clear in the next lecture actually. Okay. I'll do SSH model in a little bit more details actually. And there you will see exactly this particular question to be much more clearly addressed. That you can continuously tune the system parameter in such a way that it can convert from conventional band insulators. So conventional this phase to this phase. Okay. And we'll look at particularly look at the energy landscape. You'll see that the energy wise, energy versus k wise, they are exactly same. But then what they differ is that wave function differs. Okay. So essentially, when you say we have a energy here, that means you are solving the Schrodinger equation, right? You have a psi h psi equal to e psi, right? So this is, let's say, energy one, this is e1, and then this is e2. So h psi 2 equal to e2 psi 2 psi 1, right? You will see that depending on this phase or this phase, the wave function properties will be different in the case space, and there are other stories as well that we'll do in the next class actually. Okay, yeah. So any other questions? Actually, feel free to ask questions. Okay, this way I will also be more and more interested to, I mean, deliver lectures as well as these are essentially doubt clearing classes. Okay. Okay. I'll so let me discuss the assignment itself. Today I do not have much, I mean, uh, contents because I didn't wanted to start from SSH model on the very first day actually. I wanted to just give a brief overview of what we are going to talk about. In fact, this so far we discussed only topological insulator. It can have there can be some semi-metals as well. So what do we mean by semi-metals is that so far metals overlapping band structure so that there is always some states to conduct carry electrons, and then there are semi-metal. So all of these are sort of colloquial language, but if we really I mean want to go more deeper, since you all of us are sort of MSc or final year MSc. Uh, so for a metal, let's say I have this band. There can be very different kind of band, but simplicity. So this is energy. Now, so what we calculate is the density of states, right? At each K, what is the number of states that we have available for conduction and so on. For a metal, what really happens is that you will have some density of states. Okay. Again, this may not correspond to this actually. Okay. It's just random thing I'm trying. Uh, The essential point being key DOS is always not equal to 0. At each key point, there will be some finite DOS, density of state. So, uh, in terms of conduction, what this necessarily translate into is that at so there are enough number of available state depending, it doesn't depend on which energy you are. This actually should be energy, or rather, so this is DOS and this is energy scale. So how do you understand conduction, right? Uh, so let's say you have a system or material or metal, you are having Fermi energy, you are able to tune the Fermi energy, let's say. Okay, there are ways to tune the Fermi energy, chemical potential in the system. For two-dimensional material, it is much easier to control, but for 3D materials, you really cannot control much. Very difficult to control actually. Uh, but that's a different story. But what I'm trying to say is that let's say suppose you have a Fermi energy here, 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 here. It doesn't matter where your Fermi energy lies. You change the Fermi energy, but then always there is some finite density of states to conduct the electricity, right? So that's the more physical and more detailed way of saying the metal always carries currents. Uh, for an insulator, what really happens is that you have a bands like this. So again, this is energy, this is momentum, this is sorry, DOS, and again this is energy. You'll have some density of states here at this point, up to this point, okay, uh, and then it will actually quickly go to zero. And again here you'll start. So this is zero, and then you'll start some density of states. So DOS. Here it is non-zero. Here in this particular part, DOS is zero. So you do not have any states to carry anything. That's how you can understand that there is no electricity in sorry, conventional band insulator. And then again, DOS is non-zero. Okay. Okay. So that's the picture. So that's the more kind of advanced picture. Okay. Yeah. And then again, same thing will happen for topological insulator also. This picture will get repeated, but then we'll see that there will be edge state and so on. But okay, so we started this because to introduce the semi-metals, right? So semi-metals, what really happens in semi-metals is that we have energy and then K, uh, something like this happens. So this is actually, so this particular part, it's a exact, so this is essentially a single point. Okay. So it's a point. It's not that this something like this. Okay. Then you are in a essentially metallic region. So this is called semi-metal. Why? Because if you draw the density of state for this one, so this is, let's say, no, this will be energy and this will be DOS. So you have some energy, and then at exactly this point, your DOS is going to vanish, somewhere vanish, and then again you have some DOS. Okay. So again, DOS is non-zero. DOS is non-zero at a single particular energy, at a single particular point, your DOS is zero. Okay. So this is called semi-metal. It turns out that there are some semi-metals which are, again, the same question arises that there are some trivial semi-metals, meaning you have a DOS exactly zero at some particular energy. So this is, let's say, some E zero, okay? And you can have topological semi-metal, which again, that if you look at the density of states versus E energy, again, they will be same, but then they are different. They will show different characteristics in terms of transport experiment as well. They will not be different from a current carrying sense because both the semi-metals will carry current, but there will be other aspects, for example, surface state and so on. Okay, we'll see maybe some bit of it. Okay, so there are so the reason for saying this is that we have different topological invariants, topological index or invariants, many things. Okay, many or invariants. So first one is chart number, and then something called Z2 topological invariant, Z2 invariant, and then there is something called winding number. There are other topological invariant as well. So what this again so what this necessarily means, we'll see in the next lecture that if you plot this particular chart number, let's say Cn, okay, uh, versus let's say the phases of material. So this is let's say topological insulator phase, and then this is let's say trivial insulator. So I'll call it band insulator. Okay, Bi is band insulator, which is trivial. So what we'll see is that in the topological insulator phase, so this is some system parameter. We'll see in the next lecture there what will be this system parameter, and again it varies from system to system. Okay, you are tuning the system parameter. You are in a let's say topological, or let's say we start from a band insulator phase. So you have that Chern number, a quantity which is zero, and then suddenly for some system parameter it goes some finite value. Okay, so here it is non-zero, so not equal to zero, and this is zero. Okay, so again if we go back to the Landau paradigm of phase transition, again something similar happens, right? In a conventional phase you have a some quantity called which will be zero, but in topological insulator or non-trivial phases or topological phases combinedly, it is non-zero. Okay, uh, so it can happen to insulators. That's what we will be mostly dealing with. Okay, topological insulator, whatever we call it, quantum Hall effect is also a topological insulator. In fact, it is the first experimental observed topological insulator. Fractional quantum Hall effect is another topological insulator. We'll study quantum spin Hall effect. This will concern the spin transport in materials, some materials, which is again an insulator. All of them are insulator in a sense of they do not in a trivial phase they do not carry the current or the spin response, but then once you change some system parameter, you go back to, or you reach in a phase where there is some response which is non-trivial, which was not supposed to be there. Okay, but there are phases which are also, semi-metal, as we discussed here. Okay, so these phases which are semi-metals is called uh, topological semi-metals. Okay, uh, yeah. So it's not that only only insulators can have this kind of transition where so this kind of two phase where we'll see the difference. Rather, in the semi-metal also we can have trivial semi-metal versus topological semi-metals. In fact, the similar thing can also happen in superconductors, that you have a normal superconducting pairing. We all know BCS theory and so on, but there can be topological superconductors where BCS theory might be working, but then there are some characteristics in topological superconductors which cannot be explained or understood from the conventional superconductor superconducting theory point of view. Okay, so there are different phases and different topological materials for that. We'll see some of them in throughout these lectures actually. Okay. Okay. So far, any questions? Okay. So I'll quickly go through the assignments, week one assignments, and just tell you what to do, and then we'll end this session today a bit early. Okay. Or if you have any question, please feel free to ask. I'll be happy to answer. Okay. This will be explained actually, okay? The sir will also tell, and I will also try to do a bit, but uh, so what is the questions? Berry phase and connection. I can actually tell, but I mean, so is this a part of week 1? Let's say I'll definitely tell. So what I'm trying to say is that uh, I mean, I wanted to go with the flow of the, I mean, lectures as well, as much as I can. And this will be covered in one of the lectures, okay, actually. In fact, this is one of the most important for both the phases. I mean, topological insulator as well as quantum spin Hall insulator. Okay. Okay. So let me actually get back to the assignments. And by the way, if you have any questions and query, please feel free to write me. So this email address, and please if you plan to write, then please write at least 2 days earlier uh, to this tutorial. Okay, so if Saturday is the tutorial, at least Thursday, let's say. Okay, anyway, so the assignment 1 says the question 1, using Gauss-Bonnet theorem, find out the Euler Poincare characteristics of a sphere and a torus. Okay, so this actually covered in the lecture 1, I think 1 or 2. So what this actually tells you is that, so you have Gauss-Bonnet theorem, which says k dA equal to 2 pi chi of r. Let's say r is some parameter. Okay, and this is the Euler Poincare characteristics. So this is a part of pure mathematics actually. Okay, and then this is the so this is the genus of the surface. So this part is the Gaussian curvature. And you can write in alternate forms. Actually, this has been totally done in lectures actually. K dA equal to 2 pi 2 minus 2g, I think. Yeah. And g is called genus. One simple way to determine genus of a material is that you look at the material and so let's say we have a sphere. Okay. Sphere has genus equal to 0, and then you have something called uh, so donut or something like that. So you have a number of holes is g equal to 1, so you have a hole here, so g equal to 1. But there is a pure mathematical construct of this, but we'll not go there. G is simply the number of holes in our case, let's say. Okay, and by this you can calculate that I mean, so if you equivalent this 1 and 2, then what you have is chi of r equal to 2 minus 2g. So for sphere you have g equal to 0, so chi equal to 2. Uh, yeah, or actually we can write, so this is more easily represented. It's actually 1 minus g. So for sphere you have 1 and sorry, for sphere you have 1, and then if you have a donut or torus, for this you will have 0. Okay. Okay, so this was the simple first questions. Question number. And then the second question is sorry. Any questions? Yeah, we'll come to that. Question 4. Okay. So question 2 is the simply the derivation of Berry phase and okay. Uh, yeah, I mean I can do the derivation, but then please do this derivation from I think the best is read adiabatic approximation, I think. From Griffith's quantum mechanics. Okay. So that's the best way to derive actually. So the idea for this very phase is that suppose you starting a Hamiltonian. You have a Hamiltonian as a function of some parameter, okay? Uh, R can be any parameter of the Hamiltonian, okay? For our case, we will be dealing with solid state system, and most of the time we will be dealing with periodic system, right? We will impose periodic condition so that the block theorem applies. And for block Hamiltonians, and then we'll have block Hamiltonians as a function of k, right? K is a good quantum number, or we can also call it crystal momentum. So the parameter will usually be momentum. And one simple way how momentum changes is that any external parameter you give, you apply, let's say, electric field, the momentum changes its value, right? They gain some, I mean, they get some force, so momentum changes its value. So the momentum is the natural parameter for our case. Okay. But the way Berry formulated this problem, so the question 2 is essentially you derive the Berry phase, imagine a Hamiltonian. The question says that the general parameter is lambda. Okay, so let's use lambda. And the lambda t depends slowly on time. Okay. Uh, and then you need to derive what is the phase, Berry phase. Okay. So I'll not fully derive it, okay, because it will take almost the full time we have. But here's the key idea. Suppose you are in the parameter space. So this is, let's say, lambda t, by the way, can have multiple, I mean, multiple lambda parameters. So lambda 1t, lambda 2t, let's say, lambda 3t, and so on, right? So let's say, I mean, combination of different lambda. Just because k, just like crystal momentum, you for 3D you will have kx, ky, kz. For 2D you will have kx and ky. For 1D you will have kx or ky or kz, right? So different lambda. So I am, let's say we are working with 2 lambda. Okay. Now, what this essentially the idea of this Berry phase and so on is that you start from some point. Okay. So this is, let's say, the starting point, and you slowly changes the parameter of the Hamiltonian and come back to the same point. Okay, so that's how you traverse. And now, since we are dealing with physics, so how slowly? That's always a question, right? Slowly doesn't mean anything. So how slowly means, suppose again you will go in the energy scale picture. So suppose you have a quantum, I mean, the Hamiltonian is essentially of some quantum particle. So you have some energy levels, let's say this is an energy level, this is an energy level, and so on. Uh, Again, we'll keep referring to the solid state system case so that uh, things are more clear for our system. I mean, our cases. So let's say these are energies. So it's, let's say E1, E2, and then there are other energy E3, and they are deep. I mean, you are essentially having some insulating. So it's meaning the band do not touches each other. Okay, and you need to slowly, in a sense, that at each moment of time, so you are essentially varying lambda varying with respect to time. You are slowly, suppose you are in the energy state 3. So this is the ground state, let's say. Okay, so this is the ground state. So in this ground state, your particle is there, quantum particle, and you start from some parameter value here, and then you come back to this parameter, right? the slowly enough, what this means is that you will not change the energy state of the system. So you'll start here. I mean, you will always be in this energy state, and there is no interval transition. Meaning, you started from here, let's say in this energy, and you are not allowed to go this. Okay, so this is not allowed. So you have to evolve the system so much slowly so that the adiabatic theorem applies. Or so in simple terms, what we mean by adiabatic theorem is that at each point or each point of time, you will have some well-defined solution of the Hamiltonian so that the particle or the system have its energy as E3. It doesn't have any interval, no interval transition allowed, and each time at each instantaneous time, your h psi equal to e psi will have a well-defined solution, okay, with the same energy actually. So this is the adiabaticity. This is where the adiabaticity comes into the picture. And if you do this, you started from here and then come back here. Usually we have a, let's say, again, so you have a Hamiltonian and then psi is there, right? Now this is, let's say, at t equal to 0. Okay. Now what will be psi at t equal to at some time t, let's say t greater than 0? We'll have psi 0. So let me call it psi 0. And then e to the power minus I energy of that thing, right? E0, let's call it t by h bar. So that's the psi t. That's what the conventional, I mean, quantum mechanics tells us. What this happens in case of Berry phase is that if you like cyclically evolve the system and come back to the same point, you will have psi as a psi 0 e to the power minus I e0 t. Remember, we are at the same energy, and you will pick up some phase, extra phase. So this phase we call it dynamical phase. The phase part is this one, okay? Dynamical phase. Why it is dynamic? Because it depends on the dynamic, how fast you traverse. Because if t is less, then of course the phase will be less, and so on, right? So that's the dynamical phase, and this is called geometric phase or Berry phase. Berry phase is a bit specific because Michael Berry discovered it or talked about it extensively in a general scenario. I think in 1885. Yeah, and before that also similar phase. Sorry, similar phase appeared in optical systems, a Pancharatnam phase, or people also call it Pancharatnam Berry phase. Okay, but we will not go there. So this gamma is essentially you can write as a, I mean, you can write as a something iota how your system evolved. Let's say so you had a state psi 0 of time. So let's say put t prime and del t prime. So I'm not deriving, you just see the quantum mechanics of graphic dt prime. Okay, so far you are think so this is in terms of time integral, but then what we can do is that it can be equivalently written as 0 to some lambda state. So you started from 0, right? You started from, so here let's, sorry, so you started here, let's say with some lambda 1, and then you came back to the same point, right? Lambda 1. Now this is of course when you talk about Berry phase, it will be cyclic. So yeah, and then you can write for a cyclic phase. So this is the generic, and then for cyclic, when you come back to the same point, cyclic path, you can write as psi 0 of lambda of t, let's say, or T prime, and then del lambda psi 0 of lambda of T prime. Okay, d lambda. So you are having a phase. So this was our, wave function. If you calculate uh, applying adiabatic theorem and so on, this part was dynamical phase as usual. We know from quantum mechanics, but this extra phase is given by this. Okay, here you do not see any time dependence. Time dependence is implicit. Okay, so what this depends on is that how psi 0 changes with the lambda, right? So the integral is closed loop integral is also over lambda. Remember, lambda was a Hamiltonian parameter. So h was h of lambda of t, let's say, right? So if Hamiltonian is a parameter, lambda is a parameter of Hamiltonian, so psi is also will be a parameter of lambda, right? So this extra phase that comes when you do cyclic evolution adiabatically, this actually depends on how the wave function is, or how the wave function looks like, or what is the form of wave function in the parameter space, in the lambda space, right? And this is geometric because this sort of doesn't depend on the time or the dynamics, how fast or how slowly, as long as you follow the adiabatic theorem and adiabaticity is there. Okay, it does. So what I mean is that it doesn't depend on the total time. Okay, so it started from here and came back here, let's say t1 t2. It doesn't depend on if you go back, if you come back at time t1 or come back at time t2. Okay, it doesn't depend on that, rather it depends on the what is the path you have taken. So suppose this was path 1 and you started from same point, or let's say different point, so another point here, and here come back here. Okay, so these two paths are different, independent, by the way. This is a path 1, this is path 2, let's say. It turns out that phase, or the geometric phase for path 1, let's call it 1 and let's call it 2, gamma 1 is in general is not equal to gamma 2. Even so the important point is, even if you came back to the same point starting from this or this the same time. Okay, so let's say both of the path you traversed in the same time. So gamma, path 1 also took t1 time and path 2 also took t2 time. Just because the shape of this path or the geometry of the paths in the parameter space, this was, let's say, lambda 2 lambda 1 is different, your phase will also be different. That's why it is called geometric. Okay, and that is what is called Beery phase, and we'll see important implications of this, uh, in particular in quantum Hall effect as well as quantum anomalous Hall effect, and so on. Okay, so this is the you just need to do the derivation from the book or wherever you do it. Okay, so any questions? Okay,
Sir,
yeah, sure.
sir, is this somewhat related to what we just have studied about the topological phase transitions where
Yeah,
like,
everything is actually related, but then I mean uh, the course and the topic is so sort of, what can I say, deep or involved, that you'll slowly get a feel of it actually. Okay, we'll make an explicit connection of what is called winding number. There you will see
okay,
very similar equation to this particular equation. Okay, so the gamma. Okay, you'll see almost exactly same equation, and we'll see in the context of SSH model, and that will be in 1D. But yeah,
okay, okay.
yeah.
Sir, like we are going to solve the Suit model, like so is it with like just for 1D, right?
SSH model is for 1D, right?
Okay,
Yeah. It's a 1D polymer chain. It was motivated from a polymer actually, uh, which is existent, polyacetylene actually, which is
yes, it's like a rice mill model. I think one of the
right,
models in.
right. But we took it there, just a toy model for us, but it gives a very
Yes,
nice understanding.
yes.
Okay, third question is, Explain why time reversal operator is anti-unitary. So this you can solve actually, and it is anti-unitary because it is sort of anti-linear. Okay, so you just yeah. So for unitary operators or linear operators, you have, let's say this is A. A is an operator. You have some let's call it alpha, and then psi is some step, and then if it is unitary, then you can just extract out alpha and then you operate A on psi, right? But then for anti-unitary, let's call it B, let's say you have alpha and then psi. What you do not have is that alpha. You apply alpha is some complex parameter, okay, complex number in fact. Uh, this is not allowed, okay, so this is anti-unitary operator. You prove it, it's a part of assignment. Can actually see this why time reversal is anti-unitary just from the Schrodinger equation itself. Okay, if you apply, time reversal operator in the Schrodinger equation, you will see that the conventional way of thinking or the Schrodinger equation is not coming back. You need to get a complex conjugate actually. So for anti-unitary, what really happens is that b cap of alpha psi, it becomes alpha star psi. So there is a complex conjugation. Extra complex conjugation is needed, okay, once you want to take out alpha. And that's the difference between unitary and anti-unitary operator, and that's what you also need to do if you do Schrodinger equation, if you operate time reversal on the Schrodinger equation. Okay, the question 3b is that consider a hydrogen wave function and then with of course orbital and angular momentum, orbital angular momentum L and M. How does wave function evolve under time reversal? This I'm not solving. It's just a one-line answer discussed in the lectures itself. So someone had a question, I think. Okay, question number 4. Okay. Okay. Uh, so what was the question number 4? Sorry. Can you? I have the old assignment actually. I'm not able to access the course right now. So can anyone please copy paste the question in? I mean, at least 4 in the chat box, or even if you just tell me, it's fine. I think. So who asked it? Yeah, so Meghna, yeah. So can anyone tell what is the question for? Okay, thanks. If the Hamiltonian is invariant under time reversal symmetry and energy eigenkette is non-degenerate. Okay, okay. Then show that the corresponding energy eigenkette is real. So we have a non-degenerate energy bands. Okay, fine. And the Hamiltonian is invariant under time reversal symmetry. Okay, so I need to introduce some concept actually before solving this. Okay, so let me go. Okay, so so for conventional, I mean the time reversal operator, let's say T cap. So what it does is that if you operate this time reversal operator for one let's say set of parameters. So let's say in general I can write R is the position, okay, and then let's say momentum P, uh, you can apply it to angular momentum as well, and so on. Okay, and of course the most basic is time. So what will happen is that time reversal operator is of course it will flip the time, right, or reverse the time. Position, it will not affect anything. So R remains R. Velocity or the momentum is essentially nothing but mv, right? Even if you think classically, mv you can write as mdr dt, right? So r doesn't change sign but t changes sign, so p will be minus p, and then l is again r cross p, so p changes sign but then r also sort of remains same, so l goes to minus l, right? And then if similarly, I'm just saying it, we later we may need it. If we apply on electric field and magnetic field, then what really happens is that electric field remains same, but then magnetic field flips sign. Okay. If you want to understand it from a very basic, then electric field you can represent as a minus grad of phi, right? So it's essentially del r of phi. Phi is the potential, right? Potential function. It's our function. So potential is nothing but the potential energy, right? Potential energy is just potential energy is nothing but minus E, or in general Q into phi of R, right? So charge is a constant. Of course, it cannot change under any operation, crystalline symmetry or anything. Phi is also some, I mean, real space function. So phi r also doesn't change under time. So this particular quantity remains invariant. So E remains as E under time reversal. Okay. The magnetic field changes sign because you can think of magnetic field as a essentially current carrying loop. Let's say so. This is a current carrying loop. If you sort of uh, so this will give magnetic field along this direction. But if you switch the, I mean, time, reverse the time or operate time reversal on this current loop, it will go as like this. So in the opposite direction. So once it is opposite, then the magnetic field will also be opposite, right? So that's how you can think. There are many ways actually to how to see magnetic field. You see from the Maxwell's equation itself. Maxwell's equation are invariant under time reversal, crystal, I mean, inversion operator, and so on. So this was time reversal and spatial inversion operator. So we denote it by P. What this P means is that R, it takes R to minus R. Okay. So and then depending on, and then but T remains T under this inversion operator. So yeah, so these are the two fundamental symmetries. Now now when we say that a Hamiltonian is invariant under time reversal, or for that any matter, I mean operator. Let's say A is a general operator. General operator. When you say that a Hamiltonian or a quantity in general is is invariant under this transformation under this operator. What we essentially mean is that A, in our case, let's say we have the Hamiltonian and then A inverse or A dagger. When we deal with in general, it is sort of inverse. It is H. Okay. So this is what we mean by invariant. So the full statement is H, if H remains invariant or same, operation A. Okay, so if it is invariant, then this condition will be satisfied. So A inverse will give me back to the same H. Now the question is, if the Hamiltonian is time reversal invariant, so we have H, a Hamiltonian, and then time reversal invariant, so T inverse, we get back H. Okay, so that's the statement given. And the energy eigenkette is non-degenerate. So that is just to simplify our problems. So each have a different energy level. So let's say I mean it can be any, I mean n by n matrix, right? And there will be different energy eigenvalues, and each will have their different energy. So they are not degenerate, non-degenerate case. Okay. So the distinct eigenenergies. Now the question is, so the corresponding energy eigenkette. So let's say we have a psi1 here, psi2 here, psi3 here, and psi4 here. So if these two conditions are given, so this is, let's say, condition 1 and this is condition 2. We have a Hamiltonian which is time reversal invariant, and then we have the Hamiltonian in such a way that the energies are non-degenerate. So each eigenenergy corresponds to a distinct wave function. Okay. So what we need to show is that all psi1, psi2, psi3, psi4 are real. Okay, so this is what we need to prove. Okay, so this particular equation actually means T inverse equal to H. What it necessarily means is that I can apply T inverse T. I'm applying operator T from the right? So in quantum mechanics, it matters, as you know, from which direction I'm operating the operator. So I'm applying T operator from right. So T inverse will be, of course, unity. So TH equal to HT, right? So if that is the case, if the Hamiltonian is invariant under time reversal, what this necessarily means is that just to recharge, just a second. So TH of minus HT is 0. So this we can, of course, write in a compact form. TH or equivalently HT commutes, right? Third bracket means they commute H and T. Okay, so this is the commutator we have, given that we have invariance under time reversal. So from this equation, what we have is that, let's say psi is a general state. So we have this. So T cap. Um, so we will go back and forth. Okay, sometimes we'll write cap on operator and then we'll not write. Please, if you have any question, I mean confusion, please ask. Otherwise, we keep doing this implicit things. So this we have. Let's say we operate any operator psi. Okay. Uh, so psi is one of those eigenfunctions. So corresponding to at least one of these energy level. Let's say in general, it's psi. And what we have is that TH psi minus H of T T cap psi equal to 0. So H psi means essentially some energy, right? Energy, let's say, let's make it just E, no issue, equal to H T cap psi, right? So you can write this as H T cap psi equal to E. So this comes here because energy is real, so I don't need to put a complex conjugation, right? Uh, so okay, the point is key time reversal is an anti-unitary, so that's what you need to prove in I think question 2. So whenever we have anti-unitary operator again, so when you are applying let's say E psi, you ideally need to do E star T psi. But then energy eigenvalues are real. We have real energy, right? We are not dealing with uh, I mean complex energy. So it's real, so it doesn't matter. It comes out, and then T cap uh, psi. Let's right. So what we have is that sorry, wait a minute, mistake. Okay, no, it's fine. So from this equation, let's say, and let's say, so we had this H psi equal to E psi, right? In general. So this is let's say equation 1 and equation 2. Uh, yeah. So from equation 1 and 2, what we can say is that both psi and P psi have same energy, right? So T psi is a state. You can say that. So let's say so this part here also T psi, here also T psi. So you can effectively write this equation 2 as let's say some psi tilde, right? Psi tilde. Yeah, E psi tilde, where psi tilde is nothing but T psi. So what we have is that psi and psi tilde, which is T psi, have same energy, which is E. Now, given that we had a degenerate bands that is already given in the problem, so so here we had psi, and then what we found is that there is another state T psi which has the same energy E. What this necessarily means is that psi is exactly equivalent, or it is actually equal to T psi, right? Given the non-degenerate bands. Given the non-degenerate bands, right? So correspondingly, if we do complex conjugation of this, meaning T inverse, that means T inverse psi and as well as psi will also have the same, must be same actually. Okay, because you can construct the similar thing by, I mean, by, so I have applied, let's say, from this equation I started, right? Applying psi, but you can also write this. So I started from th minus ht equal to 0. You can start from exactly opposite equal to 0 and then apply psi, and then we can get the t inverse of psi. Okay, you can get this. So so this necessarily means is that psi, t psi and t inverse psi all are same, having an energy of E. Okay, so this will mean that t psi is also equal to t inverse psi, which t psi was equal to psi. So what this necessarily means is that if you have a time reversal operator which complex conjugate the things on which it operates, and after applying you are getting the same thing, then psi is of course real, right? when you get a number, so suppose you have a number A and you do complex conjugation, okay, complex conjugation A star, and it turns out that A equal to A star. So when you get this, when A is real, right? So that's what here happens, that psi is T psi, and you can also, so T inverse psi is also same. So this part itself tells that you operate complex conjugation which is equal to the previous version of psi. It is only possible if it is completely zero, right? So there are two possibilities. Psi itself is identically zero, but that's not where we are interested in, because we need to prove it is real. So of course zero is also you can think of, but psi is, let's say, some non-zero state, so that H psi and equal to E psi is there. So essentially psi is real. Okay. So I hope it is clear. If you have any question, ask. Okay, the last question I think was about Cramer's degeneracy. Again, this was solved in, I mean, the lectures. So yeah, not needed, I think. Yeah. Okay. Any questions?
Sir, can you repeat the A and E star part? Actually, I think my
Yeah,
internet
sure.
got lost somewhere.
So so what we got from here. So we have two things given. One is, of course, we have Hamiltonian, which is invariant under time reversal. So if it is invariant under time reversal, we know this is the condition. It should be, and that's how things are defined. Okay, if it is
Yes, sir.
invariant under any operator, it should give me same when you operate, right? So this is nothing but that. And in the operator language or quantum mechanical language, it just commutes. Time reversal operator commutes with the Hamiltonian. But we started from this equation, and then what we proved is that we already know H psi equal to E psi, right? A general, I mean, is, there are different level, let's say, and I level, let's say here it is psi, okay? Just general. I don't want it to give 1, 2, 3, 4. So we have this, and we know that there is no energy where the energy levels are degenerate. So what do you mean by degenerate is that we have the same energy for two different wave function, right? So it's, let's say,
Yes, sir.
psi 1, psi 2, or maybe something else, psi A, psi B. So they are completely different, but they have the same energy, right? Some E tilde. But that is not the case here. It is not the case here. We have been given it is non-degenerate case. So these two things are given. Now from here we can construct that uh, this is what we already know, equation 1, and then we from this we constructed that h of t psi you combinedly think as a I mean a wave function, right? So it turns out that it is also satisfying the energy E. Now given that the energy E only can have one psi, what this necessarily means is that this new wave function, which is T psi, must be equal to psi previous one, because it has the same
Yes, sir.
energy and we are in non-degenerate regime. So when if I mean, so if you write this way, it will be clear. So T psi equal to psi. What this necessarily means, you have a complex number psi, right? You have a complex number E. You operate complex conjugation. Time reversal operator necessarily, I mean, context complex conjugation. This I have not shown here, but question 2 or 3, I think, is about that. Okay, so you'll see that time reversal operator always, uh, I mean, contains complex conjugation. So you do a complex conjugation over a state psi, you come back to the same number. So this is only possible when the psi is itself totally real, right?
Yes, sir.
So that's the point.
And sir, for the T inverse part, we did the same thing, right? Like,
Yeah, T inverse,
uh,
just extended part. You don't need to show the T inverse part actually. This itself is
okay,
clear.
okay,
Psi equal to T psi.
okay. Up to that, it was clear, sir. Actually, I was asking for the T inverse part.
Oh no,
So,
it's not needed. You can show it this also. That was my
ah,
point.
okay, okay. Okay.
Okay, so any further questions? Okay, so if not, I think we can stop here. Okay, thank you for joining. We'll do more of SSH model and so on. I think the next class will be important, so please join. Okay, I'm ending the meeting.